determining a number of protons, electrons, neutrons, mass number, atomic number. We went through all of that. You turn that worksheet in, we'll grade it, and we'll see how you did as a group and individuals. So you got this periodic table, and it was put together in a way where you can kind of see the trend happening, that the smallest number starts with 1, and it goes in a consistent sequence all the way through 92 until you get down to like 56, and then it doesn't make a lot of sense after that point because it kind of drops down here. And so those are atomic numbers. And at the time they did the periodic table, there was only 60 that were known of. This whole group down here wasn't even known of. I mean, especially 58 through 71. These are actual elements. They're called the rare earth elements. And they hadn't been discovered. And then there's also some gaps in different spots that they hadn't discovered yet. But what they were doing is they were looking at atoms, and they had an instrument, and that instrument, what it did was it would divide out substances by their weight. So it was very sensitive to be able to do that. And by doing that, for example, they would put copper 63, or just copper atoms, through that device. There was 2 divisions. They seen 2 divisions that would happen. And that told them that there was 2 different atoms that made copper up, which is like, they were thinking, like Dalton, that all atoms are alike in every way. And they find out they're not. They also were able to use that instrument adapt that instrument in which to find percentages. So they were able to figure out where they were getting more of a particular weighted atom versus one that didn't have as much. And they were able to calculate that and look at that. And for example, copper has 2 isotopes. One that's heavy, 65, and one that's lighter, 63. And they were able to also determine percentages of each. So if you add those 2 together, what do you get? 100%. So 100% of the sample is made up of these 2 isotopes. Okay? Now, they're different percentages. Like if I had 10 of those atoms out here, and I start picking them up and I go through all 10, how many atoms would I get that would be 63, copper 63? 7. I'd get 7. Because it says percentage-wise, that's 7 times I would get it out. And then 3 times. You guys ever watch the weather? 70% chance, pretty good for rain. Pretty good. Pretty good chance. 10%, not so good. Not so good. Maybe some places will get rain, but most of the places aren't going to get any rain. So if I have a sample and I have 70% of the sample of a certain isotope, the more I take from that sample, the more I get of that one that has a higher percentage. Okay? So they tested all of these elements, and they were able to determine all of them certain percentages and certain weights. Okay? Now I need to tell you a little bit about the weight and how the weight came about. So these are what we call relative weights. They don't have a unit. They don't have a gram. They're not kilogram. They're not microgram. What they are weights that they can relate to one another. So we know an atom's weight is really small, right? Okay. If you would do the scientific notation, it'd be times 10 to the minus 27th. Okay. So really, really small in weight. So what they said is that we're going to go ahead and relate all these weights, and we're going to give it a unit, and we're going to call it atomic mass unit. So the atom's mass in its unit, in its relative unit. So if you look at that page, there's one isotope on page 82 that does not have any decimals. You guys find that one? Carbon-12. Carbon is the most common, I think it's the most common atom that there is, or one of the most common atoms, isotopes. And so they said by definition that weight of that one is 12 units. 12 atomic mass units. Kind of like this meter stick is 1 meter. 1 meter. So everything's related to this meter stick. When I want to find millimeters or centimeters or kilometers, everything's related to that unit. So carbon is the unit, that weight, everything's related to. So if I take 1/12 of carbon's atomic mass unit, I come up with 1 AMU. And so then they are able to compare everything to carbon-12, and that's how they come up with all these different kind of weights. And they're called the relative weight atomic mass units. Later on, we'll use grams, and we'll explain why we can use grams later on. But these are atomic mass units, and they don't really have a unit like mass that we would think. They're all relative masses. Okay? So if you notice, there is a weight up here. And that weight is, there's just one weight. Over here I have 2 weights. Copper-63 has a weight. Copper-65 has a weight. But up here, there's an atomic mass that has 1 weight. And we use that weight all the time. You'll get sick of using that weight. Okay, so, oh, do I have to use that weight again? We always use that weight. All right? So, how do they come up with that weight? Well, they tell you, laid down on that reading. How did they come up with that weight? What did they do? How did they calculate it? Yes?
They take the percentage in decimals times the mass and,
Yep.
and
So,
add them to the other one.
and then they add them up. So they have 2 of them. They'll get 2 weight. They'll get 2 weights that they add together, and that gets their average. So what they did was what I'm going to show you here is taking place, and this is a little bit more descriptive than it's on that page. So what they do is they say, I'm going to take the decimal form of the percent. You got to take the decimal form. You can't take 69 times 62. You can't take 30.85 times 64.928 and add them together and expect to get the average weight. Because the average weight should fall between 63 and 65. If I take the actual percent and multiply it, I'm going to get an answer that's 6,355. That's not halfway in between 62.93 and 64.928. So what you have to do is you have to divide everyone by 100. Okay? If I make free throws 5 out of 10, okay, what's my percentage? 50%. Okay? So if I continue with that percentage and shoot 100, how many will I make? 50. Okay? So to figure that out, you would take it times the decimal form. You would go 0.5 times 100. What's 0.5 times 100? Right? Half, but it'd be 50, right? You wouldn't take 50 times 100, because then you would get 5,000. Okay? You didn't make 5,000 shots. You made 50. So you have to take the decimal form. Okay? So automatically take these, move the decimal 2 places to the left, or divide by 100, does the same thing. You get your answer. Questions on that? If you guys want to write that down, just this part, why don't you do that? Because what happens, I noticed in 5th period, they didn't write it down, and then when it came to do a practice problem, they didn't have that screen to look at, because I can't switch it back. So go ahead and write that down. These are, we would label this average atomic mass. So when we label this, to solve for a particular weight of a substance, it would be atomic mass. If I say average atomic mass and atomic mass, I mean the same thing. So the atomic mass. So go ahead and write that down. And then I'm going to give you the next screen, and I'm going to go ahead and have you do a practice problem. I'm going to go ahead and advance the slide, and you guys can practice what you just have written down. So, neon 20, there's 90.48% of it. So, guess what the weight's going to be close to? 20. I mean, when you look at this weight, when you find an average, if you got something like 90% of that weight, it's going to be really, really close to that weight when you do a calculation. So you kind of already know that it's going to be 20 point something probably. Okay, these other ones are going to cause it to get a little bit bigger, but they're not very big percentages. Neon 21 is 0.27%, and neon 22 is 9.25%. So, let's have you attempt to calculate the atomic weight of neon. Okay? Based upon that other example with copper 63 and copper 65. Okay? See what you get. These are nines. These are all nines. It's hard for me to write with that every once in a while. So this is 19.992, 20.994, and 21.991. So go ahead and count. You'll have to do one of these on the test. Okay? You'll have to do one of these on the test. So what we're doing is we're finding atomic mass for that element. So I'm going to go ahead and give you a third one to do. Now that you see the numbers and how they work out. And then you go ahead and put that in your notes too. So here's the third one. Strontium 84, strontium 86, strontium 87, and strontium 88. Does anybody have an idea about what the weight is going to be on this? Can you guys predict what the weight's going to be?
Somewhere around 80.
So it's close to 88. This is 87, rounded. So I would probably think a lot of it, this kind of skew it down, so probably, maybe in the 87 range, low 87 maybe, just guessing. So you guys will be able to figure it out here in a second. But go ahead and do the actual calculation. Again, my nines kind of get goofy, but these are all nines. Okay? There. If you can't tell what it is and it looks like a 7 or a 9, it's a 9. Now this is a 7, of course. Okay? So go ahead and do that one and see what you get.